Hello, welcome to Nano Energy and Catalysis Lab Research Talk. I am T.S. Shridharan. I am going to present on the topic of highly active photothermal materials of bismuth copper oxychalcogenide for efficient solar desalination. This work is just recently submitted for publication. So these are the contents I'm going to discuss in this research talk. First, I will introduce what is solar desalination and why solar desalination is important. Next, moving on to the mechanism involved in solar desalination. So this consists of three types. First is the photothermal materials, which is used for solar desalination. Then phenomena of water evaporation, that is how water is getting evaporated on the surface or from the bulk of water. Then we move on to the properties of photothermal materials. And moving on to the photothermal materials, we have different classification of photothermal materials. So among that, they have disadvantages and advantages for them. And for the solar desalination, we need a new class of materials. So as a new class of materials, we will be introducing a layered oxychalcogenide material, that is the BCSO. Then how is the synthesis of BCSO nanosheets is done, and material characterization, solar desalination performance, and the summary. Introduction to solar desalination. So mainly we talk about water crisis in the world, which is the biggest problem. So water crisis is the lack of fresh water resources to meet the standard water demands. The world's water resource include 97% of seawater, 3% of fresh water. According to the predictions by the World Resource, at least 3.5 billion people, or two-thirds of the world's population in the world, will likely experience water shortage by 2025, and also 1 out of 11 people lack access to clean water. This is a problem for both developing nations and developed nations. Consumption of poor quality of water can lead to adverse health effects. And also, global warming plays a major role in increase of water scarcity as localized climate changes. So what is solar desalination? Solar desalination or solar thermal desalination is a technique to produce water with low salt concentration from seawater or brine using solar energy. So there are two commonly methods of solar desalination, either by directly using the heat from the sun or using electricity generated by solar cells to power a membrane process. Why it is important for solar desalination? So solar desalination is primarily a zero carbon emission process. That is, the advancement in solar technology enables overcoming previously existing problems like dust and high temperatures, which affected the efficiency of previously used solar panels. So this solar desalination uses free solar energy for operation. And moving on, solar desalination plants are inexpensive, light in weight, and are easy to transport from one place to another place. The plants can be set up easily either offshore or onshore, and the maintenance cost is very low and it is environmentally friendly. Mechanism involved in solar desalination. Solar energy appears to be realistic and long-term solution to world's persistent concern of water constraint. However, photothermal materials are frequently used to enhance the natural process of solar-driven evaporation. So, the materials which can efficiently absorb light and convert them into heat energy is called photothermal materials. So, what are the main phenomena involved in the solar desalination process? That is, water evaporation process. The first process consists of absorption of solar radiation and conversion into thermal energy. The second process generates vapor from the absorbed heat energy. The third process consists of the conversion of water vapors to form water. Moving on to the properties of photothermal materials for solar thermal desalination. So the photothermal material should behave like perfect black body, that is, it should have strong and broad light absorbing properties. It should have high photothermal conversion and low thermal conductivity to minimizes the heat loss, and it should be easily contact with the surface water, that is hydrophilic, and also it should be floatable, and it should have microporous structures through which the steam generated can be easily escaped through microporous channels. Classification of photothermal materials. Photothermal materials can be classified into three different categories, that is plasmonic materials, carbon materials, and semiconductor based materials. So the plasmonic materials consist of silver, gold, platinum, etc. The main advantages of the photothermal plasmonic materials are high photothermal conversion and high light absorption. In the meantime, the drawbacks are it is hard to fabricate and the cost of the plasmonic materials are very high. The carbon-based materials include graphite, graphene, carbon nanotubes, and carbonized materials. So the main advantages are they are abundant in source and it has high light absorption efficiency, and compared to the plasmonic materials, it is relatively low cost. Then moving on to the disadvantages, the heat emissivity or the thermal conductivity is very high in case of carbon-based materials, and they also require more hydrophilic treatment before the solar desalination process. Semiconductor based materials consist of two different types like sulfide materials and oxide materials. Both of these materials have tunable band gap, high photothermal conversion efficiency, and they are highly hydrophilic, but they have insufficient light absorption and complex synthesis or fabrication process is required to make the photothermal absorber material, and they also have high thermal conductivity, and some of the materials have poor stability in contact with water. Why we need a new class of materials for solar desalination? Currently, the interfacial solar desalination or solar thermal desalination has been considered as a promising solution for wastewater treatment and water purification. At this, the photothermal absorber material, as we discussed previously, enables solar light absorption, photon to thermal energy conversion, and water evaporation. So this plays a crucial role. However, the absorber's material, low absorption and high thermal conductivity are the primary concern that contribute to poor performance of the solar desalination, that is low conversion efficiency of the photothermal materials. Nonetheless, there have been much progress on thermal management strategies of desalination setup to improve the efficiency by reducing heat loss. But there is a lack of research in developing potential absorber materials to fulfill the requirement. Consequently, it is necessary to find an alternative and new class of materials that compensate for low thermal conductivity and high light absorption properties. Bismuth copper oxysulfide as a photothermal material for solar desalination. Bismuth copper oxysulfide, in short BCSO, is a oxysulfide material which has similar layered crystal structure and band gap with bismuth copper oxyselenide and lanthanum copper oxysulfide. So these type of oxychalcogenide material have high potential in energy conversion due to the intrinsically low thermal conductivity, tunable band gap, and long-term environmental stability. The properties of BCSO include the band gap is very low as 1.2 eV, then low thermal conductivity of 0.9 watt per meter Kelvin, and it has high photothermal conversion efficiency. So why we incorporate BCSO for solar desalination? Mainly because of the low thermal conductivity and simple wet chemical synthesis for producing BCSO, and high light absorption and photothermal properties. So also, the BCSO is highly hydrophilic in nature, which adds as an additional factor to be used in the solar desalination. These are the main reasons why we incorporate BCSO for solar desalination. Synthesis of BCSO nanosheets via hydrothermal method. The process of synthesizing layered BCSO nanosheets via pressure-induced hydrothermal method is shown here. So the copper and bismuth nitrates were dissolved in DI water, followed by the addition of thiourea and sodium hydroxide as a sulfur source and metal precipitating agent. After stirring for 30 minutes, the dark brown solution is transferred into a Teflon-lined autoclave and is maintained at 160 degrees Celsius for 12 hours. The BCSO nanosheets were finally obtained by repeatedly washing the BCSO precipitate or suspension with DI water and finally with ethanol and drying it in a hotter oven overnight. Material characterization. The obtained BCSO was characterized with X-ray diffraction to confirm the phase formation. So we obtained pure phase BCSO with tetragonal crystal structure with no impurity peaks. Also, the SEM images shown here shows that the BCSO has dense morphology, nanosheet morphology with an average lateral size of 100 nanometers. From the TEM analysis, the BCSO has square-shaped nanosheet morphology with flat and smooth surfaces as shown here. The average size and thickness of the nanosheets were observed to be 100 nanometer and 12 nanometer respectively. Also, from the STEM analysis, the bismuth to oxygen and copper to sulfur layers were arranged in a tetragonal symmetry without any defects. Furthermore, the bond length of bismuth to oxygen, bismuth to bismuth, and the interlayer distance were determined to be 2.4 angstrom, 3.8 angstrom, and 8.5 angstrom, which is consistent with the theoretical calculation values. The light absorption property of a photothermal absorber material is a critical factor affecting the efficiency of solar steam generation. So, we performed the UV-Vis spectroscopy and thermal conductivity measurements for BCSO nanosheets. The absorbance spectra of the BCSO nanosheets were measured over the wavelength range of 200 to 1200 nanometers. As shown in the figure, the BCSO show broad light absorbance from ultraviolet to the near infrared region, which implies high light absorption property of BCSO. Also, the absorption band edge is at 1040 nanometer. From the tau plot, we calculated the band gap and was found to be 1.19 eV. The thermal conductivity measurements of the BCSO was found to be 0.99 watt per meter Kelvin, which is as low and is very favorable for solar desalination process. Preparation of BCSO photothermal absorber and solar desalination setup. A polyurethane substrate was used to coat the BCSO nanosheets using dip coating method. The BCSO nanosheets were uniformly coated on the top surface of the PU sponge substrate. A digital photograph of the BCSO nanosheet coated PU sponge substrate is displayed here. Also, from the SEM image, we can see that a homogeneous coating of BCSO nanosheets was observed without any cracks or breakage, and the average thickness of the BCSO layer coating on the PU sponge substrate was found to be 4 micrometer. Solar desalination setup using regulated 1D water pathway. With the BCSO coated PU sponge substrate, a solar desalination setup was designed, which is shown here, where the water channel, that is cotton wick, provided a continuous regulated water supply from the bulk water to the BCSO photothermal absorber layer via capillary action. Additionally, the polystyrene foam acts as a thermal insulating layer to prevent the direct heat and evaporation of bulk water. Solar steam generation performance. After preparing the solar desalination setup, the water evaporation performance of the BCSO nanosheets was evaluated by measuring the time-dependent mass change under stimulated sunlight illumination of one sun. 4 samples, that is bulk water, pristine PU substrate, and BCSO coated PU sponge substrate and graphite coated PU sponge substrate were tested for comparison. The graphite coated PU sponge substrate is taken as a controlled sample. After 60 minutes of illumination, the water mass change of the BCSO, graphite, bulk water and pristine PU were found to be 1.77, 1.06, 0.31 and 0.07 kg per meter square respectively. Significantly, the BCSO coated PU sponge substrate exhibited superior evaporation performance compared to the other samples. The corresponding evaporation rates and efficiency of other sample is shown here. The evaporation rate was calculated from the slope of water mass change curves. Overall, the BCSO achieved a highest evaporation rate of 1.77 kg per meter square per hour. The efficiency of the solar-driven evaporation was calculated using the formula eta is equal to mhlv by QICOPT, where eta is the solar conversion efficiency, m is the stable evaporation rate, HLV is the liquid to phase conversion enthalpy, which is 2.250 kilojoules per gram. QI is the normalized solar intensity, that is 1 kilowatt per meter square, and COPT is the multiple of solar illumination. The efficiency of BCSO was calculated to be 96.1%, which is 5 times and 1.4 times higher than that of bulk water and graphite evaporation efficiencies respectively. Long-term stability of BCSO photothermal absorber. The long-term evaporation stability of BCSO was tested for 10 hours under continuous illumination. So we observed that there was no change in the water mass or efficiency. Also, we tested the real seawater samples collected from Busan for solar desalination. The ion concentrations of sodium, magnesium, calcium and potassium were decreased significantly, which are far below the WHO, that is World Health Organization, drinking standards. Conclusively, combining the high efficiency desalination with strong light absorption properties makes BCSO as a promising photothermal material for interfacial solar desalination. Furthermore, we analyzed the photothermal behavior of BCSO under one-sun illumination. For this, the wet state rise in temperature of BCSO and control sample graphite were recorded using an IR camera. So, the wet state surface temperature of BCSO rapidly increased to 45 degrees C, but in contrast, the temperature of the graphite gradually increased to 40 degrees C. This result is consistent with the thermal conductivity values, which is given as an inset figure. To conclude the photothermal effect of BCSO on interfacial solar desalination setup, a schematic representation is provided here, wherein the BCSO show low heat conduction and strong light absorption and superior wettability properties. To summarize, the layered oxychalcogenides of BCSO are promising photothermal materials for efficient interfacial solar desalination. The BCSO nanosheets were successfully synthesized through pressure-induced hydrothermal method. These nanosheets show strong light absorption in the UV-Vis NIR range and also show low thermal conductivity with excellent wettability and high photothermal conversion. The 1D water path with regulated water supply and porous PU sponge substrate enable the excellent water evaporation rate of 1.77 kg per meter square with a steam generation efficiency of 96%. Furthermore, the long-term performance of BCSO nanosheets remain unaltered even after 10 hours of continuous evaporation. Additionally, the BCSO showed high water purification performance and excellent ion rejection capabilities, which corresponds to the drinking water standards recommended by World Health Organization. Finally, the oxychalcogenide material offers a promising platform for the design of cost-effective and high-performance solar desalination systems owing to the facile synthesis method, high light absorption, and low thermal conductivity. My sincere thanks to my Professor In Sancho, Dr. Sivanandam Armugam, and Min Che Kang for the guidance and support throughout my project. Thank you for your kind attention. Kamsamida.